Hi there everyone. Today we're going to look at continuing our good work from last lesson on differentiating complex curves when we have these negative powers. So first off, let's see what you can remember. Pause the video and see if you can match the blue with the black. Right, so hopefully you've had a go and you're going to get a nice warm fuzzy feeling if you get these right. If you've just had a really bad 2 or 3 minutes, then don't worry, we're going to explain it again and hopefully it will all make sense. So the secret really is to be able to write this in another way. So for example, this is the same. So when we multiply fractions, we times the top, and then we times the bottoms. But the bottom in this case would be a 1, which I don't normally write in, but to make this point I will. So that's exactly the same. Now if you can do that, 3 over 1, well that's just 3, isn't it? And this is the only thing you need to remember, is they are equivalent. Now if you need to, you can put a 1 there, and that might make it easier. Because if there's a 1 as a denominator, when you flip it over, so now there's a 1 there technically, the power goes minus. So you can see that they match. Let's have a look at this one. So this is the same. So it's 3 times 1 over x squared, for the same reasons as I just explained. That's the hardest step, and once you've got that, you should be okay. So that's 3 times this. Right, well, look, we have a squared here. If we want it to be at the top, we have to change the sign. So that is that one. Now, this is a slightly different one because the 3 is now on the bottom, and there's a 1 on the top. But, if you think about it, there was a 1 there, because 3 divided by 1 is 3, and 3 divided by 1 is 3. I just repeated myself. So there was a 1, we just don't think about it being a 1, but we only start thinking about the number when it's not 1, so actually nothing has changed. It's that. So it's 1/3 times x to the power of minus 1. And here's a neat way of thinking about it. See that 3? It's on the top, and it stays on the top if you wrote this as a fraction. This 3 is a denominator. It's a denominator there, and it's still a denominator. So numbers that are on the top, they stay at the top. Numbers are at the bottom, they stay at the bottom. So this one's easier. This is just x to the power of minus 3. Just move up to the top, change the power to be negative. So there we have it. Hopefully you've had loads of success, and if not, we're still going to explain it as we go through. So here's a complicated looking function. It's like a type of reciprocal graph, but it's kind of hard to imagine. Now, find the gradient when x is 2. Well, to find the gradient, we need to find dy by dx. That's our gradient function. But we can only do that when every single term is written in the form ax to the n, and we have a problem here. So we have to rewrite. So that is equal to this. Numbers on the top, it stays on the top. If this was a fraction, it would be on the top. There's a 1 there, make it negative. Now, this is where people go wrong. They differentiate that, they put a 3 there, and they differentiate in half and rewriting half. Please don't do that. If you write a y equals, these two lines have to be equivalent. But now we can differentiate. So times by the power, minus 6, reduce the power by 1, times by the power, you can put 1 there if you like, reduce the power by 1, x to the power of 0 is going to go, so just lose the x. Now, you can just sub x into here for 2, so sub that x for 2, type it into your calculator, but if you can, I really would urge you to see if you can put it back into this form. So it's a negative power, now it's positive if you put it on the bottom. So I'm going to use that one. When x is 2, dy by dx is equal to minus 6 over 2 squared, which is 4, plus 3. Well, that's the same as minus 3 over 2 plus 3, or 3 take away 1.5, we end up with 1.5. Let's have a look at another. So, well, even uglier function. we've got some squareds on the bottom here, but this is nothing to worry about. This is all in the form x to the n. We can differentiate that with our eyes closed. This one, we've got to change it. So 3's on top, it stays on top. X to the power of 2, well, if we move it up, the 2 has got to be negative, and we're just going to pop those on again. We need the gradient function to find gradients. That's the gradient function, dy by dx. So let's differentiate. So minus 6 x to the minus 3 plus 4. Just times by the power, reduce the power by 1. Remember, x terms, you lose the x. No x terms, just lose the whole term. That written better, negative power, put it on the bottom, it's a positive power. That's on the top, it stays on the top. So when x is 3, what do we get? We have minus 6 over 27 plus 4. But they're both in the 3 times table, so I'm going to say that's minus 2 over 9, and that's definitely easier for me. So 4 whole ones, take away 2 ninths, we're going to have 3 and 7 ninths. All non-calculator really, but you probably would want to use it if you kept it in that form. So try not to. Don't be lazy. Push your brain. Okay, here's another one. Now, this one, this is exactly the same, but why I was hesitating there is, let's just change this for a minute. Let's say it says find the gradient at minus 1, and they give you a coordinate. Well, they're going to give you a y value in here as well. They're not going to just leave it blank like I have. So let's do that. So if we sub in minus 1 into here, we get y. So minus 1 cubed is minus 1, so that would equal to be minus 1. Minus 1 squared is actually 1, times 2 is 2. So 1 add 2. So the point I'm trying to make is the first two, they told you when x is equal to something, you only subbed in this. Or they could actually give you the coordinate. So let's see how I change my answer in a minute. Right, this is a pretty easy one. There's nothing to worry about with the 1 there. So I've now rewritten it. I found my gradient function. So we get minus 3x to the minus 4 plus 4x. I rewrite it if you can. Okay. So when x is minus 1, you can see it didn't matter that I changed it. I did exactly the same thing, because are there any y's in here? No, so you can't use that. The only thing we have is x's, so the only thing I'm interested in is the x's. It's just the way we change the question, and that often freaks people out of it. Right, so minus 1 to any power, even power, sorry, is just 1. So we end up with minus 3. Plus 4 lots of minus 1. Minus 3, take away 4, is minus 7. One more to look at. This is we're going to twist it on its head like you were doing 2 lessons ago. So we have a function. It's not in the form x to the n, so we're going to have to change that. But this time we're finding where the gradient is minus 1. So we're trying to find the actual location. So y is equal to 9x to the minus 1 plus 4. That's a rewrite in the form ax to the n. Differentiate to find the gradient function. So we have minus 9 x to the minus 2, and that's gone. So we can rewrite that as minus 9, negative at the top, positive down below. But this time we want to know the gradient, so we want to know where the gradient is minus 1. So we just change that to be minus 1. X squared is our denominator, so let's times by x squared. We get minus x squared. I'm going to put minus 1x squared to make it easier to explain. To get x squared on its own, we now need to divide by minus 1. So we just get 9. Which means x is plus or minus 3 when we square root. So it happens at 3 and another location, and it also happens at minus 3. So let's pop a 3 in here. 9 divided by 3 is 3, plus 4 is 7, so it happens at 3, 7. If we put minus 3 in here, we get minus 3 plus 4 is 1. So there are 2 points on this function where the gradient is -1, and there they are. Right, that's it. Best of luck, get practicing, and I wish you all the best.